his research is mainly on dependability and software-based replication. So,
thanks, Nicola. Thanks you all for attending. So in fact, before getting to the technical talk, I thought I'd tell you a few words about the place where I come from, because you may not all have heard of this place. So I'm a professor at the Università della Svizzera Italiana, which sometimes is translated as University of Lugano, although it's not really correct, because there is also a campus in Mendrisio, another city. And it's in the canton of Ticino. The university is of this buildings you can see here. It's in downtown Lugano. Just in case, so Lugano is south of Switzerland. And actually, the University of Lugano makes part of the Swiss university system with 10 cantonal universities and 2 federal universities. So we have here the ETH and EPFL, and all the others are cantonal universities. So the computer science department, or informatics, as you call it, is located in the campus. It looks like this big hard disk, and it's the 4th faculty of the University of Lugano, and it started actually recently in October 2004. We were 6 professors back then and 8 PhD students, and it has grown quite quickly. Today we are 21 professors and about 100 PhD students. And it's in terms of funding, is the 3rd largest after the 2 polytechnical schools, ETH and EPFL. So Nicolas, we have 2 bachelor courses in informatics and computational science, 7 master programs and a PhD program. And Nicolas said it already. So my own research at USI, it's on distributed systems and distributed data management systems. We do mainly systems work and also a little bit of algorithms these days. And my group has 5 PhD students. Okay, so that's it for the introduction. Let me now jump to the technical talk. So I will tell you about some work that was very recent in the group, and in the concerns high-throughput atomic broadcast protocols. So this was jointly done with my PhD student Parisa, Nicola, at the time he was in Lugano, and another student who is now working at Apple in the US. So this is an outline. I'm going to introduce this work and tell you about the system model, what the assumptions we make, and so Ring Paxos itself, the protocol that we propose. A lot of related work, because this is a very so many works have addressed similar problem. The performance evaluation that we performed, and then we conclude the talk. So let me start by making a statement that I believe that very few of you are trying to refute. So replication is important for fault tolerance. I'm not saying it's only for fault tolerance, but in the context of this work, is mainly for that. And if you're doing replication, there are 2 basic techniques to actually keep consistency. So I'm interested in replication with strong consistency. So although there are many different algorithms, they all boil down to different kind of models. Active replication, sometimes called state machine replication, or passive replication with primary backup. So this talk is about state machine replication. So in a single slide, to define state machine replication, all the replicas, they start with the same initial state of the service and replicating, and you apply all the same set of commands in all these replicas and in the same order, and then therefore they are going to proceed through the same set of states. So although I don't have in the slide here, one of the assumptions of state machine replication is that the execution of the commands is deterministic. That's why executing the commands, the same command in the same order, is going to lead us to the same set of states at each replica. Well, it turns out that these 2 requirements here, so applying the set of commands, the same set of commands, and in the same order, I can characterize this by a communication primitive, which is sometimes known as atomic broadcast or total order broadcast. So this basically is an abstraction. It's one way of encapsulating the 2 properties that I mentioned before. So atomic broadcast, it guarantees 2 properties. The first one is agreement. So if a process delivers a message, you can also read this as one of the replicas executes the command, then all the other correct processes or all the other replicas are also going to deliver or execute this command. And total order basically means that all the replicas are going to execute these commands in the same order. So the goal of this work is basically to implement a high-throughput atomic broadcast protocol. It's how to guarantee these two properties that I presented before with very high throughput. So now I just told you about what we are trying to do, right? I'm going to spend some time telling you about the environment in which we did this work, so the environment that was targeted by this work. The first assumption is that we consider communication by message passing only, which basically this means is we are not doing this, we do not assume that there is a physical memory shared by the processes. And so in the communication, the message passing communication, we assume two different kind of primitives. One is that allows us to do one-to-one communication, and the other one is one-to-many, right, which basically translates into IP multicast. So the assumptions are not strong with respect to the communication itself. Messages can be lost, they can be reordered, but we assume that they cannot be corrupted. And we focus on the crash recovery failure model. Processes, they can crash, they can recover, but what is implicitly assumed in this property is that we are not targeting Byzantine behaviors. So the processes, either they do what they are supposed to do, or they don't do anything at all, right? But they don't try to be malicious and break the protocol. And the system is partially synchronous, by which I mean that, so to guarantee the former properties, I don't, in safety, that they are not violated, I don't need any synchronous assumptions. I can assume that my processes, they execute at any speed, and the message can take an arbitrarily long time to be delivered, if they are delivered at all. But I can only guarantee that something good happens in the system, that messages get delivered, if there are some minimal assumptions about the synchrony, which basically means how long it takes for a process to execute some step, and how long it takes to actually deliver a message. So this is only needed to prove liveness properties, the termination of the protocol. It's not needed for safety. So if these synchrony assumptions are violated, the protocol is not going to behave incorrectly, meaning processes are not going to deliver messages in different orders. Okay, so let me tell you about Ring Paxos, the protocol that we developed. So Ring Paxos, it's based on Paxos, right? Lamport's total order protocol, and several very practical observations. So basically, what we did was, in a few words, you took the Paxos algorithm, and then we applied simple practical observations to turn this algorithm into a high throughput one. So what are these observations? The first one is, so if you compare IP multicast versus Unicast, and I have a single sender, one process sending messages to a set of destinations, and these destinations varying from 1 up to 25, what you can see is the following. So in this graph here, on the x-axis I have the number of receivers, and the y-axis I have the maximum throughput that each receiver can get. So if I have, so there are two lines, right? One is I'm doing the communication through IP multicast, and the other one is through Unicast. So it's pretty obvious that, so the dashed line is Unicast. If I'm sending to a single process, I can reach throughputs that are close to the maximum allowed by the network, which is 1 gigabit in this case. But as soon as I have a higher number of receivers, I have to distribute my outgoing bandwidth, and then basically the processes are going to receive less information. Now, if I do this with IP multicast, I'm basically delegated to the switch or the infrastructure, the actually sending of the messages, and it can sustain much higher throughput, almost regardless of the number of receivers. So this has a number of fine prints, right? It assumes here that all my receivers are connected to the same network switch, and the switch can actually it's good enough to handle IP multicast in an efficient way. So that's the first observation. It's quite simple. So in these experiments here, without tuning too much, really, the experiments we managed to get more than 900 megabits per second, while with 25 receivers it goes down to 35. So that's the first observation. IP multicast is preferred over several Unicasts. So IP multicast it's unreliable, right? It's based on best effort. So the question here is really how we can minimize message loss. As I said before, our protocol, it can tolerate message loss, but the performance is really is best if they don't happen, because if messages get lost, some mechanism is needed to actually retrieve, to recover these messages. So we better avoid message loss if you can, although the protocol can tolerate them. And what you do here is some pretty simple flow control and some management of socket buffers. I will say more about this later in the talk when I mention this experimental setup. So that's one of the things that was done to reduce the number of lost messages, but not only that. So if I take multiple processes doing IP multicast, what I observe is the following. Since there is no flow control, if I have multiple processes IP multicasting messages, what may happen is that, and depending on the rate at which they do this, right, you can have conflicting messages being sent at the same time, and there's a danger that my buffers get full and messages get lost. So what you did in this experiment here was to run a similar experiment. The sender, one or more senders, try to send as much information to the receivers as possible. So the number of receivers here is fixed. I don't really remember how many we had, but I think it was like 15. It doesn't really matter. But what happens is that the more receivers I have simultaneously IP multicasting messages, if I want to minimize my number of lost packets, I have to be conservative and reduce the rate of sending from these processes. Now, I don't have the problem with a single receiver. There's one guy here that can really send as much as almost 900, a little bit more than 900 megabits per second, and then only after that I start having some lost messages. But I have lost messages much earlier if I have more senders. So at an aggregated sending rate of 400 megabits per second, it doesn't really matter how many receivers I have. But as this increases, I start having more lost packages. And as I said before, the protocol can handle it, but it's going to degrade the overall throughput. So the third observation is one multicast sender. I can achieve higher throughputs if I have a single multicast sender. And finally, the other optimization, the other aspect that Ring Paxos takes into account is the following. If I have multiple senders, right, sending small messages to a single receiver, once I present you the protocol, it's going to be clear why this is an important aspect. So if I have any senders, one receiver, and I want to minimize the overhead on the receiver, I can communicate basically in two ways. So I can actually have each sender sending its small message to the receiver, which is not good, because the receiver gets to actually, there's some more overhead involved. The receiver has to receive all these 3 messages. Or I can do it in the following way. I can have one process sending the small message to the next, which is going to append its own message to the next, and so on. And eventually, the last one sends the whole thing in a single message. So what I'm reducing here, I'm actually reducing 2 things in this scenario here. I have a single message being received, right? There is less overhead at the communication level, and there is a single context switch in the process that's receiving all these messages. So this pattern of communication is preferable to the first one. So the ring overlay reduces the overhead. So Ring Paxos basically is all these observations put together in the context of the Paxos algorithm. That's pretty much what it is. And it turns out that by doing this, we can reach levels of throughput that were unseen in any Paxos implementations. So let me tell you a little bit about the Paxos algorithm, really not much, but only that I can explain more in detail how Ring Paxos works. So Paxos, it decomposes the processes in 3 agents. So you have the proposers, the process that send the messages, the commands, in the state machine replication, if you will. And the learners, these are the processes that receive these commands and execute. So the state of the application actually residing here. The proposers are like the clients of this service. And then we have the guys in the middle, which are the ones who define the order of these messages. So for example, in a single, so Paxos is a sequence of instances. In a single instance, what happens is it gets the message from all the proposers and decides, so the acceptors decide one of these messages, and they are sent to the learners. So the similarities between Ring Paxos and Paxos, the most important one is that Ring Paxos, it shares the same reliability as Paxos. And this is an important thing because Paxos is an optimal algorithm in terms of communication steps, in terms of resilience. So there is no other protocol that can tolerate, under the same assumptions, can tolerate the same number of failures. So it's the same reliability as Paxos. So we also have learners, acceptors, and proposers. And there's also the notion of a fixed coordinator, which is basically, very quickly, is one acceptor, right? It's chosen among the acceptors. And this is the process that defines the order. There's one process that tells the order, and the other acceptors, they confirm the order with the coordinator. As I said, the coordinator is an acceptor. So let me compare here the two algorithms. And what I'm going to show on the Paxos execution is really an optimized implementation of Paxos, as proposed by Les Lumpert in his original papers. So we have the proposers who send their values to the acceptors, so actually to the coordinator, one of the selected acceptors. The acceptor, the coordinator, gives the order of this message, and then sends this order to the other acceptors. This is known as a phase 2A message. Okay, it's 2A because there is a phase 1, which is basically it's an initialization, if you will. It's only needed if you change the coordinator, right? So in normal execution, you don't actually have to do this. You can execute before you are sending the messages. So they don't count for the throughput. It's only initialization. The acceptors receive this message, and in the normal situation, they confirm the order that's proposed by the coordinator, and they tell the learners that they have confirmed this order. As soon as the learners have a majority of acknowledgements or phase 2B messages, they can deliver the message. So the condition here to deliver a message is receiving a majority of 2A messages from the acceptors. So that's how Paxos works, generally speaking. So Ring Paxos works in a slightly different way. So important thing here is, for example, if you would implement this using IP multicast, right, you'd have 2 IP multicasts, one per acceptor, if you want to maximize the throughput, which, as we saw before, is not good. So Ring Paxos works like this. Proposers, they also send their values to the coordinator, and the coordinator instead, it sends a 2A message to everyone, to the acceptors and also to the learners, right? When the learners get this message here, they don't really know what to do with it because the message, the order, hasn't been confirmed by the other acceptors. They know though that there's some good chances that this message here is going to be delivered in the order it is received, because as I said before, unless there are multiple coordinators simultaneously, we can actually Paxos tolerates the order that the coordinator is proposing is going to be confirmed. And that's where the ring comes into play. Once the acceptors receive the 2A message with the message content, the first acceptor, or actually the second acceptor in my list, it sends a 2B message, not to all the learners or to the coordinator, but it sends to the next acceptor in the list. And the next one is going to send to the next, and so on, until eventually the message reaches the first one, the coordinator, which knows that now a number of acceptors have agreed actually to deliver this message in this order. And then what the coordinator does, it sends the decision to everyone using another IP multicast. So what we have achieved here is, so there's a single process doing IP multicasts, is the coordinator. The communication, these acknowledgements here, which are usually very small messages, just saying, okay, we agree with this order. They do not cause many interruptions at the coordinator because they are sent through a ring. And then this message here actually carries information saying, well, all the acceptors have agreed with this message. You can go ahead and you can send the decision. So there are some other optimizations which I'll discuss later. But as you can imagine already, so Paxos is a sequence of these instances. So after this decision here, what's going to come next is another instance of 2A methods with the values. So you can actually batch all these things here. In reality, I don't have a special IP multicast with decision. I have them batched with my next phase 2A messages. So let me show you. So actually here, so there's a single IP multicaster. So this is a small animation that shows actually how the protocol works. So we have the proposer sending the message to the acceptor. The acceptor gets it and then assigns a sequence number, and then stores the message in a buffer. The reason why it stores the message in a buffer is because, in addition to all the things I told you before, we also batch multiple messages if they are small. And then IP multicasts the message to everyone. They all get it, and they store in a buffer. Now, they store it in a buffer because they don't really know whether this order here is going to be confirmed or not. But as I said before, the first acceptor in the ring, or the one that precedes the coordinator, is going to send its acknowledgement to the next acceptor, it's going to add to this its own acknowledgement, and eventually the message reaches the coordinator. When it has enough acknowledgements, it knows that this message here can be delivered. So it waits for the next message to be received from a proposer. It's going to assign a sequence number as before, buffer it, and then it's going to take the message and the acknowledgements for the previous message and send to everyone. So when the learners and the acceptors receive this message, they can deliver the previous one, and then they store the number 13 in the buffer, and then it goes on. And that's how the protocol works. So it's a very simple idea, actually. But it turns out that it allows us to get very high throughput, as I'll show next. But before I get to that, let me just comment on some of the properties of Ring Paxos. So the coordinator, it's the one that forms the ring. So someone has to take the list of acceptors and define this ring overlay. It's basically overlay. It's how they're going to communicate. This is delegated to the coordinator. And it's the last node in the ring for obvious reasons, right? It's the one that's going to actually send the notification, the decision notification at the end. So the messages that are exchanged among the acceptors in the ring, they are actually just IDs. Obviously, I don't send the message contents because these ones have been sent already originally by the coordinator. This is sometimes called indirect consensus. And then the decisions are multicast to all. Okay, I mentioned that already. Now, another thing is, so I briefly mentioned that Paxos is an optimum with respect to resilience. It requires a majority of acceptors to define the order of the message. So if you have n acceptors, you need n plus 1 over 2 to accept it. Obviously, you only place a majority in the ring. You don't have to place all of them. And with this, we reduce the latency of the protocol a little bit. So the proposed values, the actually message contents, are disseminated through the phase 2A, is the first message that the coordinator IP multicasts. And the first acceptor in the ring is the one that starts the 2B messages, the acknowledgements. So a number of optimizations. Phase 1 can be done. So the phase 1 is the part that I didn't show in the protocol, is this initialization that is done whenever I change the coordinator. This one can be batched for a number of consensus and done actually right after the coordinator is elected. So that's why it doesn't count for the latency of the protocol. So we don't claim any novelty here. This was discussed by Lamport when he actually proposed the Paxos algorithm. But we use it. Now we do batch for phase 2 messages, as I mentioned before. So not only batch multiple values in a single phase 2 message, but also batch the decisions together with phase 2 messages. So I remind you that we are trying to optimize throughput without degrading latency too much, but the really goal here is to maximize throughput, and therefore there is no way of avoid batching. We also have multiple concurrent instances of consensus. We don't have to wait for one to terminate to start the other. We start them all a sequence of instances to also maximize throughput. And when I commented this already, the decisions are picked back to the next IP multicast value. So you may be wondering, so this is, I'm describing actually the best case when everything goes right, but actually things not always go right. And we have to handle coordinator failures, for example, what happens if the coordinator fails. So these are detected by the acceptors, which are going to elect a new coordinator. And because, so Ring Paxos doesn't change Paxos in any aspect that's fundamental, the safety is guaranteed even if there are multiple, at some point there are multiple coordinators in the system. They decide to do things in parallel. The protocol is still resilient. Nothing bad is going to happen. And this is due to the actual original Paxos properties. I can also have lost messages. Right? It can happen that a message gets lost in the ring from one acceptor to the other. In such a case, what's going to happen is the coordinator is going to wait for some time until it gets the acknowledgements from all the acceptors. If the one doesn't arrive for a certain time, it simply assumes that some message was lost by the acceptors and it resends it. Now, of course, if the coordinator also suspects that one of the acceptors has failed, he has to redeploy the ring and then resend the message. Okay, so as I said. Now, there are also some chances that messages get lost at the learners, right? So the way this is handled is, if the learner sees a gap, so it receives message number 13 but doesn't receive message 12, it suspects that, well, something wrong happened. And the way we handle this in Ring Paxos is by having the learners ask some of the acceptors for a retransmission. So they try to avoid contacting the coordinator because as you may guess by now, the coordinator is really the most loaded process in this system. I have numbers to show you later. So instead of asking the coordinator, they ask some acceptors. And you can also distribute the learners among the many acceptors. Okay, so that's it for the protocol. I'm not going to give you any more details. You can clarify doubts later if you want. Let me tell you a little bit about the related work, and I will do this in a quick way. So there's been a lot that done in the context of atomic broadcast protocols. It's a theme that has been largely studied. You can, I guess, if you had to guess, there must be more than 60 different algorithms. Now, very few of these have been actually implemented, and they try to optimize different things. Right? They can be actually classified according to a number of parameters, like, for example, a known classification is the one I'm showing here. Kind of groups the algorithm in different ways. So to a certain extent, Ring Paxos it would be like a fixed sequencer, although it doesn't really fit very well any one of these categories. Now, what I have here is some known algorithms that either they are in this list because they have very good throughput as well. It's the case of LCR, not relatively recent compared to the others. It has very good throughput, right? But it's different than Ring Paxos in a number of ways that we discuss in experiments. Another very famous or maybe known protocol is Spread. Maybe some of you have heard. So Spread is it exists as open source and is used in several projects that rely on replication. It's based on the totem single ring approach. Now, other approaches that are somehow similar, Ring plus FD, which is I cited here because it also uses a ring. And the last two are two implementations of Paxos. The first one is Paxos. It's only based on IP multicast. And the last one is it's all based on point-to-point communication. So there are two extremes of the spectrum. So a quick comparison between all these algorithms, and Ring Paxos here is at the bottom. What I can see is that, so in terms of communication steps, for a certain number of failures, it's not necessarily better than the other protocols. I mean, you can have tolerate very few failures. And in terms of number of processes, it's also not necessarily the best protocol. So LCR can do with fewer processes. Only F is the number of tolerated failures in my system. So LCR can do with fewer processes than the Ring Paxos. The difference is that LCR is based on much stronger assumptions than Ring Paxos. What I mean by stronger assumptions is basically I cannot tolerate any failure suspicion mistakes. So I'm assuming stronger synchronous assumptions. I can have to determine with certain precision how long it takes for processes to execute and how long it takes for messages to be transmitted. And if I get this wrong, I may actually deliver messages in wrong order. So the assumptions here are stronger than needed here. Now, so I guess what really matters, we took these protocols and we actually implemented the ones that were not available and used the ones that were publicly available to compare to Ring Paxos. So the comparison that I'm going to show next, we assume basically no disk writes because that's the way some of these protocols work. Ring Paxos can be turned actually to use to write on disk either synchronously or asynchronously. But the data that I'm going to show you next does not write to disk in none of the protocols. I'm assuming also a best case, which is hopefully the most common case, no faults. So the experiments were run from 3 to 10 times in the average. For Ring Paxos, I'm assuming packets of 8K, and also a buffer to keep all the methods has 1/6 megabytes, and the network is 1 gigabit. So this is the first graph. It kind of it's throughput, so bits per second, with respect to the number of receivers. So I'm comparing the 5 protocols that I showed you before. So the graph kind of separates these protocols in 3 groups. So we have Ring Paxos and LCR on the top. Then we have Spread. So this is the y-axis is log scale. So we have Spread coming next, and then finally I have Paxos and Paxos for system builders. So these are the other Paxos implementations. So there are a few things you can see from this graph. So the first one is that the only ones that really get close to the theoretical limit are Ring Paxos and LCR. And they are pretty stable, right, with respect to the number of receivers. LCR, the particularity about this protocol is it places every process in a ring, not only a subset of them. And it doesn't use IP multicast. So the only way to actually get this level of throughput without relying on IP multicast is by placing all processes in a ring for a very simple reason, right? Because I can use the incoming throughput and outgoing throughput of each process. And in doing that, I can actually get really close to that. But if I don't do this, the only other way is by using IP multicast. It can actually be seen from the other systems. So spread does not use IP multicast, and so the performance degrades as increased number of receivers, and Paxos for system builders doesn't use it either. Now, Paxos does use IP multicast, but every process, so it's an implementation that's closer to the original Paxos protocol, plus the fact that every communication is through IP multicast. So it has pretty stable throughput, but because we have several processes actually sending these messages, I cannot send messages at a very high rate. Otherwise, I have too many message losses. That's why it is basically the lower end of the graph. I can also look at these algorithms not by the number of bits per second, but also the number of messages that each one sends. But although so we try to fine-tune these protocols to get best performance for each one of them. So they have used different packet size. As I said, Ring Paxos uses the best results were obtained with 8K packets. LCR, for example, to get the best results, we have to increase the packet size. So a consequence is that I send fewer messages. And it is the same. So the pattern of this curves here, it closely follows the previous one. But it shows the size of the messages that actually give us the best throughput, as it was shown first. Now, what I'm going to do next is I'm going to concentrate on Ring Paxos and on LCR, because these are the two ones that actually reach the highest throughput. Okay, so this table here basically sums up all the protocols by showing, by using a metric that we call MTE, is the maximum throughput efficiency. This basically what it does is it tells you how the protocol is doing with respect to the capacity of the network, right? So since we're running our algorithms in a 1 gigabit per second network, the closer can get 1 gigabit, the higher the MTE. LCR and Ring Paxos get 90%. So LCR is not constant, as I showed before. We got here the best value, which is a little higher than Ring Paxos. All the other protocols, they have a much lower maximum throughput efficiency. So let's have a look at the scalability of these two protocols, and this is another difference between Ring Paxos and the competition. So with respect to throughput, they up to 25 receivers, they have a similar throughput, although for a small number of receivers, LCR is better. But the problem with LCR is, besides the stronger synchronous assumption, is that since it places all the learners in the ring, right, the latency of this, so the average latency per learner, it increases linearly with the size of the ring, right? That's pretty obvious, which doesn't happen with Ring Paxos. There is a degradation, a little bit, and this is basically due to how the switch handles IP multicast. Now, we have run a whole bunch of other experiments, and I'm going to tell you briefly about this. The first one is the impact of message size. So there's clearly, and this concerns only Ring Paxos. For bigger messages, so it can get actually higher throughput, and the latency doesn't change much. So that's why we set in all the experiments the messages to 8K. So this graph here, it's basically a little bit more complicated to understand. The experiments are the same as the ones that I showed in the previous graph, and so as I have fewer messages, so every messages are smaller, right? I need more messages to be sent in order to reach a higher throughput. As the size of my message increases to the right, I need fewer messages to be actually sent per time unit. And the same here is, so here's the size of the message with respect to the size of a single packet. So we are sending packets which are 8K. If my messages are of size 8K as well, so I'm sending one packet per message. Otherwise, I'm sending fewer packets per time unit because I have to actually form a bigger message until it is sent. There's also some influence from the socket buffer size, although so it does have an impact on the throughput and the latency. But as you can see, the scale here it's from 800 to 900, so the difference is not as big as you would think first by looking at the picture. But there is a difference. So if you set smaller socket buffers, you're going to have less throughput. This is in part due to the fact that you have more lost messages and have to do more retransmissions, and in the latency as well. So what we did was in the experiment that I showed you before, we set socket buffer size to 32 megabytes. Now, I guess a more important fact is really how CPU is used in all these protocols. So we have the four roles, right? We have the proposers, which basically send the messages, and in their case, they have so they don't do anything other than sending these messages. So it uses 37% of the CPU. The coordinator is the one that uses most of the CPU, so 88%. Acceptors don't seem to be a big problem, and the learners are not a problem either. So, but the coordinator is really the part to concentrate. So that's why if you would send messages, for example, from the acceptors to the coordinator using another communication pattern, chances are that you wouldn't actually reach the same level of throughput. So to conclude, so Ring Paxos has constant throughput based on the Ring on the IP multicast, and it doesn't add much in terms of latency. Besides, it inherits from Paxos, the resilience of Paxos, which is, once again, it's an optimal protocol. It cannot do better than that. Now, it has this. The system has been implemented actually, and it's available as open source. It has received some interest since it was not published very long ago. It had a number of downloads. What I found out is that it was a good portion of these downloads come from China. I don't know if that means anything. So that was what I had here. I don't know if you guys would be happy to answer any questions or clarifications of things.
The acceptors, why do they have to agree on a certain sequence? Because this seems to be the whole problem, that a group of machines has to agree on a sequence.
Yeah, so they have to agree on the sequence number, which in other words is they have to agree on the order of these messages, right?
And why why do the acceptors have to know about the sequence number? The coordinator could just push the data to the learners in some arbitrary sequence.
Yeah, that's so they have to agree on the order. Actually, they have to agree on the order of the messages, right? To make sure that if a coordinator fails and another one is elected, the new one is not going to contradict what the previous one did. So that's pretty much what they are doing there. And the reason why a majority is because if there is a majority, right, you can crash these acceptors in any way. There's always going to be one that remembers what the coordinator did, and then the new coordinator can actually learn, or the new one learns what the previous one did. This is actually what happens in phase one, which I was very quick. This initialization for each coordinator is to learn what the previous one did by means of the acceptors. So that's why. Yep.
What happens if you have a packet loss in the multicast?
Yeah, so a packet loss at the multicast. Let me show the protocol because I think it's. Yeah. So you can have anyone can lose a message here, right? Except if the acceptors lose a message here, then so the first acceptor loses the message to never send the phase to A bit because it doesn't know about the message. So the second one is not to send it either, and then the coordinator is never going to receive the confirmation, right? So the way you handle this is after you send this message here, it starts a timer. If it doesn't receive a confirmation after some time, then it resends the original message
To everyone.
to everyone. Yes, through an IP multicast. It could be because it actually doesn't know who doesn't have it, right? It just knows that it didn't receive the confirmation, so it resends. So that's for the acceptors. Now you can have messages lost by a learner. So this message here, what's going to happen is the next time the learner receives a message, you can detect that there is a gap, and then it's going to ask for a retransmission from the acceptors. Yes.
What happens if one of the machines in the acceptor ring goes down, and how does the system respond to that failure?
So you have to constantly monitor. So the coordinator has to monitor the other machines to know whether they're working or not. So if the coordinator suspects that one of the acceptors went down, it has to replace this one by another one. So
go back to phase 1 and redo the ring?
No, not necessarily. So here you only have a majority of the acceptors in the ring. So it means that we have 2 other spare machines, right? Because it's the protocol is 2F plus 1. So if I want to tolerate 2 failures, I need 5 machines. But I don't have to place all the 5 in the ring. Actually, I don't even want to do that. So if it suspects that one has crashed, what it does simply is it redoes the ring, right? Some local information, and then re-multicasts the message. So it doesn't have to go through phase 1 again, because it's the same coordinator. So phase 1 only is executed if the coordinator changes.
And in the event of a failure, one of the acceptors, how long does it take for the system to get back to stable state?
It depends on your timeouts. Now, this is there's no magic answer here, right? You really have a trade-off. You can be very aggressive with your timeouts and try to react very quickly to failures, but then you may make mistakes because maybe you're just too slow, and then you're going to actually redo the ring and resend the message. Actually, what we're really losing here, because redoing the ring costs nothing, it's a local information. The real cost here is resending this 2A message because it thinks that one of the acceptors has crashed. But it can be made arbitrarily short and then risking more retransmissions. So in reality, these messages here, they are rarely lost. And that's the reason why you can get to throughputs which are close to 1 gigabit, because most of the time these suites, they don't typically lose the messages. The lost messages are basically due to buffer overflows, because they are sending too much and the process didn't have time to actually remove them from the buffer. So in reality, it happens very rarely. So we set here the experience the timeout kind of large. Now, I didn't say, nobody asked, what happens if this message here gets lost? So nobody detects it, right? So the way to handle this, typically, proposers, they are also learners. So when they propose a message, they also set a timeout, and they wait, a timer, and they wait to eventually deliver this message. And if they don't do it, they deduce that, well, the message was lost at this part here, and then they retransmit it.
So you said that the learners can identify message losses due to gaps in sequence numbers,
right,
which in theory would imply that the acceptors keep an infinite number of buffers. Because
yes.
So do you have any idea or numbers? I guess you have ring buffers there as well, so trade-offs.
Yeah, that's true. We assume a monotonically increasing sequence number, yeah. But with like 32 bits or 64 bits for the sequence numbers, which you can send quite a lot.
No, sure, but I mean, have you any idea of how frequent these losses are? So, right?
Yeah, so that's what I said before. So the losses, right, message losses, they in an environment like this, right? It was done for so it's a local area network. Yes, you can stack the switches if you want, and if your system administration allows you to do IP multicast, right? But it's a confined environment. It's not the internet. So messages, they get lost because the processes, they're not fast enough to remove the message from their buffers, right? They get overwritten. Otherwise, they don't really get lost because modern suites.
Right. But for the learners, I could expect that these are, when in practice, these are machines that have, I know, they go down for maintenance and stuff like that.
Right.
So there, I could imagine that actually the downtime is much bigger than acceptors.
Yeah. So that's a different kind of problem. So if the machine goes down for maintenance and then takes some time, then we're talking about a different kind of recovery, right? Which this mechanism here is not really what we want to do.
So you would do the kind of full state recovery.
Right.
Yeah.
Exactly. You also have you have to take checkpoints from time to time,
sure.
Because otherwise these buffers, so these lists here, they keep growing forever, right?
Sure. I mean, yeah.
But you're right. At some point, yeah. So if it's a maintenance, then you actually take an image and then replay from the image the rest that you are missing. But it's a different kind of mechanism. But it's a good point. So yeah.
more questions. So thanks again.
Thank you.